Hello and welcome to our webcast. In this session you will see how you can use LabVIEW FPGA module with the Xilinx SPARTAN-3E Academic Program Board plugin to directly program the SPARTAN-3E FPGA from Xilinx. LabVIEW is an ideal platform for programming and teaching the concepts of digital logic. With its inherent data flow programming paradigm and true parallelism, LabVIEW code naturally maps to the power of the Xilinx FPGA technologies. LabVIEW FPGA also supports the ability to link in existing VHDL code. As you can see in the slide, LabVIEW FPGA includes the HDL node, which allows you to easily paste in existing code which will be compiled with your application. What I'd like to do now is to build a simple application. But first, let's review. Using the Xilinx Webpack toolchain, let's build a very simple application that toggles an LED upon selection of a switch. In this application, you'll see that we define an LED. We then will use that local variable in a traditional loop to flash the LED upon the selection of a switch. At this point, let's tie the specific pin we wish to control that is connected to the LED within our application. Now we will compile and build our application. What I'd like to do now is show you the same example using LabVIEW FPGA and the plugin module for the SPARTAN-3E board. We will create a new project and then select a target that we wish to control and program. In this case, you'll see that the SPARTAN-3E is automatically populated within the New Target and Devices menu. What we'll do next is we will add I/O resources that we wish to control that exist on the SPARTAN-3E evaluation board. In the pop-up dialog, you will see all of the resources that exist on the SPARTAN-3E evaluation board. Each of these resources are tied specifically to an FPGA pin. With this nice dialog, LabVIEW FPGA and the SPARTAN-3E plugin allow you to very simply select the resources you wish to control within your LabVIEW application. As you can see, those resources are automatically added to our project. Next, I'd like to create a new program that utilizes these resources. In this example, we wish to create a while loop, and in this while loop, we will toggle our LED upon selection of a switch. And as you can see here, we've placed a Boolean false to the edge of a while loop. And you'll also notice a structure on the left and right of the while loop. This is known as a shift register and is used to keep the state of data from one iteration of the loop to the next. And in this case, we will feed a false statement to our Boolean not structure, and then upon executing the inverse of our Boolean logic, the while loop will execute once more utilizing the reciprocal value. We also place a false statement onto the edge of the while loop to indicate to the structure that we wish it to execute indefinitely. Next, let's drag our resources over to our program. As you can see here, we are going to connect our LED to one side of our Boolean not. We also create a virtual indicator that will execute up on the host and communicate by way of JTAG down to the live running target. As you see here, we connect a traditional structure such that when the switch is on, the code inside the true statement will execute, and when the switch is off, the false statement will execute and nothing will happen. We also wire, as you see with switch 0, another virtual control up on our host PC. Here is our virtual control and virtual indicator. This indicator and control is connected in real time by way of JTAG directly to our hardware board with its running code. When I click on the Go arrow, LabVIEW will automatically create the necessary VHDL code and compile the application. But first, let's add some timing. LabVIEW has very extensive timing control for your FPGA application. And in this case, instead of operating at the nanosecond or the tick count, I wish to control this while loop and control it to operate once every 500 milliseconds. Our while loop will execute once, wait 500 milliseconds, and then execute again. At this point, our code is compiling using the integrated Xilinx toolchain, and will automatically create the bit stream and download the code to the FPGA. Upon download, the code will automatically begin running. What you see here is a dialog that gives you a status of the compilation process with complete details of the Xilinx toolchain. You also receive a summary compilation report to give you an indication of the amount of FPGA resources utilized. Next, the program immediately runs, and you'll notice that the LED indicator begins to blink on and off when the switch is depressed. What you see here is the live virtual indicator and control that operates on the host PC and is communicating by way of JTAG directly to the hardware target. In review, you can see how LabVIEW is very intuitive with the graphical data flow programming, and how LabVIEW block diagrams natively map to FPGA logic. And it's very easy to see how your application is executing. This picture shows a live representation of our evaluation board. As the switch is moved, you'll see that the LED indicator begins to flash. And at the same time, you'll note that our virtual indicator and control executing on our host PC also are updated. Creating multiple instances of LabVIEW code is very simple in LabVIEW FPGA by simply just copying a while loop, for example, and pasting that on your diagram. LabVIEW FPGA will compile both while loops and download those directly to FPGA silicon. We've only touched upon the multitude of functions, structures, constants, and IP blocks that are available to you within LabVIEW FPGA for programming the Spartan-3E starter board. LabVIEW FPGA is the ideal platform for teaching the fundamentals of digital logic and the power of Xilinx FPGA technologies. I encourage you to learn more about LabVIEW FPGA through the ni.com website and to download the Spartan-3E target for LabVIEW FPGA module.